Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. We will continue today with the topic of size reduction, and we have started this in our last class where we have discussed about the introduction related to the requirement of size reduction, the objective of size reduction in the food processing and industrial scale of food processing operation, and we have also learned that how to define particulate solid and how to define a single particle in a mixture of a bulk solid, what are the different equivalent diameter, by that we can express the particles in a bulk mixture. And also we have learned this concept that there is a need to identify the distribution of particles in the bulk solid mixture, because not a single size is available mostly in case of this the size reduction operation or this bulk solid. So, there is a distribution of different size is available most of the time, and we need to find that what is the predominant size fraction in that mixture. So, we will today discuss in detail the particle size distribution, and also there are other topics in the list of this particular chapter that we will cover with due course of time. Now, we will start particle size distribution today. So, as in the last class, if you remember that there are different kind of equivalent diameter when we have expressed, that is based on the sieve size opening through which the particular diameter of the particle should pass, or equivalent diameter particle should pass, or we have seen the based on the settling velocity, or based on the size fraction we can differentiate. So, there are many methods to identify different particle sizes or to find the distribution of particle sizes. The very common one is the microscopic analysis, by which the different sizes can be easily separated. There are other methods, one is elutriation, settling or sedimentation, and there is laser diffraction. Based on that also we define the equivalent diameter, and the most common one and easiest one is the sieve analysis. And in the sieve analysis also there are many standard sieves are available, one of which is the Taylor series, which is the US standard based, and in that if we consider the distribution based on the sieve analysis, what we do is we keep the product on the perforated screens or sieves, and then there are certain sequence of steps are there that we put a stack of the sieves and then we vibrate it for a certain amount of time. So, what will happen that the particle sizes which is lower than the equivalent diameter of that perforation or the opening of the perforation will come down to the next lower fraction of the sieve, and which is the bigger one will retained on the upper sieve. Now, what happened that in most of the time 100% efficiency may not be reached. So, some fraction of the particle may retain on the sieve, on the upper sieve, and some will pass through. So, those will retain on the sieve may have fraction of the particle which is having the size lower than the opening of the screen, but even though they will not pass through the screen. So, what happened that the efficiency of the screening is defined as the ratio of the mass of material which passes the screen to that which is capable of passing, right. So, some fraction which is capable of passing, but the ratio of the mass which is actually passed through. So, define the efficiency of screening. Okay. So, this is an important parameter in understanding the particle size distribution. So, efficiency is based on the size of the material. Okay. What will be the size fraction? Based on that the efficiency is defined. It may be assumed that the rate of passage of the particle of a given size through the screen is proportional to the number or mass of the particle size on the screen at any instant. So, this is important because this will form our basis of analyzing the different particle size. So, what it says that it is assumed that the rate of passage of particle of a given size through the screen is proportional to the number or mass of particles of that size on the screen at any instant. Okay. So, if we want to express this in terms of a mathematical expression, let us consider that W is the mass of particle, mass of a particular size on the screen at any time t, then we can write dW by dt, that is equal to minus k into W. That means, dW by dt will be proportional to the W, that is the mass retained on a sieve, on a particular sieve at any instant, and since with time this will reduce, we have kept a minus sign here. K is the constant for a given size and shape of the particle and for a given screen. So, this is how the rate of passage of a particle we can define. So, then mass of a particle, if we consider in this fashion, that is W1 is the mass retained on a particular size of screen or sieve at an instant when t equal to 0, and after time t if the mass is reduced to W2. Okay. So, the mass which is already passed through will be W1 minus W2, which is passing the screen at any time. Okay. So, if this is happening, then we can write that ln of W2 by W1, that is equal to minus k into t. So, that means it is exponentially reducing the number of the mass fraction of the mass of the material on a particular sieve is reducing in a fashion of exponential decay curve on a particular size of the screen. So, W2 that is remaining at any time will be W1 into e to the power minus kt, well k will depend on a particular size of the sieve and the material. Now, a quantitative indication of the mean size is important, and quantitative indication is in the sense that what are the different fraction and what is the mean size, I mean the size which is dominating in the fraction. So, we need to define the mixture in terms of that particular size, and the result of a size analysis can most conveniently be represented by means of a cumulative mass fraction. So, cumulative mass fraction curve in which the proportion of the particle x smaller than a size d is plotted against the size d. So, this is the curve. Okay. So, this is cumulative mass fraction, x is showing the cumulative mass fraction. So, if we consider that at any instant the x fraction which is smaller than the size d. So, as we move from 0 to the higher size, if any instant we reach, so the fraction which is the left side of that will indicate that the size smaller than that particular size d. Okay. So, here this representation is a result of the sieve analysis, which is cumulative one. Okay. So, we have added the fraction which is larger than this particular size d. So, then further we can say that if we take the size frequency curve, size frequency in the sense the fraction of having a particular size dd. So, if we take the size frequency curve and then plot with respect to the size d. So, this is the curve, the slope of dx by dt, the slope of the previous curve that we have drawn with respect to the fraction, cumulative fraction with the particular size d. So, the slope of that curve when we have plotted with respect to the particular size, we are getting this curve which is called the size frequency curve. Okay. This is called the size frequency curve. So, there are many benefit of this curve. This can tell us many things, that one is the most frequently occurring size is then can be shown by the maximum of this curve. Okay. So, the fraction we are getting at maximum point. So, here the frequency is higher, that means the particle size of this particular fraction will be higher mass fraction in the whole distribution. So, for naturally occurring material, the curve will generally have a single peak, and for mixture of the particle there may be as many peak as components in the mixture. So, what happened that when there are different mixtures are there, so different compositions are there, so those have different size fraction. So, it may happen that in one lot one particular size is having dominated. So, we may get different or more than one peak in the frequency curve, size frequency distribution curve. Now, if the particles are formed by crushing larger particles, the curve may have two peaks. One is the characteristics of the material, because the material has a certain orientation, and upon getting a similar kind of force, they have a tendency to break in a definite size. Okay. So, other is the characteristics of the equipment. So, the way the force is coming, it will have a tendency to make the particle in a definite kind of shape. So, because of these two, we may get two definite high frequency plot in this frequency curve. Now, mean particle size. So, now we will see that we need to express one particular size to express the lot of a distributed bulk particulate solid material, and this expression of the particle size of a powder or granular material in terms of a single linear dimension is often required. Okay. So, considering that, because we have taken that single linear dimension is equivalent diameter most of the time. So, considering all particles are of same size, unit mass of particle consisting of N1 particle of characteristic dimension d1 constituting a mass fraction x1, similarly N2 particle of size d2 constituting the mass fraction of x2 and so on, is the basis of determining the particular size, because we will assume that the each fraction will have which is passed through, let us say, a particular sieve. So, that means those having lesser size than this particular opening of the screen. So, similarly, a particular size linear dimension has been fixed, which is dimension d1, d2 etc. for each fraction x1, x2 etc., and the number of those particle also is defined as N1, N2 like that. So, then we can express that suppose x1, that one fraction now we want to express, which is having the size of d1. So, x1 will be n1 k1 d1 cube into rho s. What is this? d1 is the dimension. So, when we want to express in terms of the volume, so linear dimension cube we need to express. So, k1 into d1 cube is defining the volume of one particular material, okay, one particular particle. Now, n1 number of particle is there. So, multiplied with n1 give the volume of all the particle, n1 particle into rho s, which is the density. So, we are getting the mass fraction of the particle in that. Now, suppose all summation if we do, I mean all fraction. So, summation of x1. So, all the fractions will constitute 1, which is the whole amount of the material, and there the rho s and k1 will be similar. Rho s is the density, k1 will be the constant parameter which is based on the particular sieve and the material, and summation of n1 d1 cube, in the sense there may be different fraction and of different number. So, those are we are summing them here. So, that means n1, if we want to calculate from this equation, n1, which is the number of particle, that will be 1 by rho s k1 into rho s k1 into x1, the fraction, divided by d1 cube. Okay. So, this is important that n1, the number of particle in of d1 dimension in the fraction x1 will be 1 upon rho s k1 into x1 by d1 cube. Okay. So, now if the size distribution can be represented by a continuous function, then instead of x, now we write dx. Okay. So, dx, the continuous fraction, if we take very small amount of increment in that. So, ds fraction, because of the dn number of particle, if that fraction increase by ds amount, so that is because of number of dn increase in that size. So, that will be dx equal to rho s into k1 d cube into dn. So, dx by dn we can write rho s k1 into d cube, and if this dx, now we can integrate from fraction 0 to 1. So, when all the fraction will become of that particular size. So, we can write 0 to 1 dx equal to rho s k1 into integration d cube dn. So, rho s is the density of the particle, k1 is depend on it's a constant, and its value depends on the shape of the particle. Okay. So, this is how we can represent the size distribution in a continuous function. Now, different mean particle size we will explain now. First one is the volume mean diameter dV. So, volume mean diameter is expressed as dV equal to integration 0 to 1 d dx divided by 0 to 1 dx, that is equal to integration 0 to 1 d into dx. So, d is the particular diameter or the dimension, and dx is the mass fraction that is increasing, that is of particular size d. Expressing this relation in finite difference form, we can write dV equal to summation of d1 x1 by x1, summation x1, that is summation x1 d1. So, d1 is a particular dimension, x1 is the mass fraction of that particular dimension. Now, in terms of particle numbers, if you want to express rather than the mass fraction, so dV will be volume mean diameter. So, it will be dimension d1 into the dx fraction that we had. So, ds fraction, we remember that x1, when we try to express the mass fraction x1, we represented in a way where there was rho s k1 into n1 into d1 cube. So, now with that it will be d1 to the power 4, because the concept is d into dx by the by integration dx. So, that will be rho s into k1 n1 into d1 cube. So, finally, we are getting summation of n1 d1 to the power 4 by summation n1 d1 cube. So, this ratio will give you the volume mean diameter dV. Okay. So, all whenever we want to express the particle numbers in the form of the particle number, we will recall the previous previous expression and try to relate with that. So, the previous expression was, so for dx you remember this one, or for x1, okay, n1 k1 d1 cube into rho s. Now, when we converted it to dx, so that time we will convert this to d1, and this concept we will use every time whenever we try to express in terms of number distribution of the particle, right. So, we were in the volume mean diameter. So, this is the expression dV summation n1 d1 4 divided by summation n1 d1 cube. Now, next will be mean volume diameter dV dash, which is represented as this way. Suppose we have the dimension dV dash, which is the mean volume diameter. So, k1 into dV dash cube, that will be of the representing the volume of one particle multiplied with the summation n1, that is the all number of particle in that. So, that volume will be equated to all the fractions of the particle. So, summation k1 n1 d1 cube, and finally, we are getting dV dash as cube root over summation n1 d1 cube divided by summation n1. Now, also we can write it in this form of mass fraction basis, that is cube root over summation x1, because x1 relates the number of particle into dimension cube. x1 is the mass fraction and all other thing density and k will be cancelled. So, we can represent this as summation of x1. Now, n1 will be then x1 by d1 cube. Okay. So, then we can write in cube root over 1 by summation x1 divided by d1 cube, because summation x1 is the combination of all fraction that leads to 1. So, finally, the mean volume diameter dV dash can be represented by this formula, cube root over 1 by summation x1 by d1 cube. Now, if instead of the fraction of the total mass, the surface area in each fraction is plotted against the size. If you remember, we have plotted this in the particular size d, and the cumulative mass fraction we have taken as x, okay, and then we have plotted. Now, instead of x we can plot the surface area also, okay. We can plot the surface area A, or we can represent it by S, etc. Okay. So, if we do so, that instead of a fraction of the total mass, if the surface in each fraction is plotted against size, then a similar curve is obtained, although the mean abscissa ds is then the surface mean diameter. So, the size d that we have obtained, that will be here the surface mean diameter, right. So, if we plot the surface area with respect to the diameter, okay, of the different particle. So, the mean abscissa ds that will get, that will represent the surface mean diameter. Now, what will be the expression for that? That will be ds equal to summation n1 d1 s1 divided by n1 into s1. So, that is equal to n1 k2 into d1 cube divided by n1 k2 into d1 square. because S1 is what surface area, we know surface area will be proportional to square of the linear dimension. So, we can write K2 into d1 square and multiplied with d1, that will be d1 cube divided by n1 into S1. So, surface area of all the particles that we are getting. Okay. So, that is why n1 K2 into d1 square, that is equal to summation n1 d1 cube divided by n1 d1 square. So, ideally is that if the surface area is S1, okay, surface area is S1 and number of particle is N1 and the uniform surface area is ds. So, that will be equivalent with all the different fraction that we are having N1 d1 with S1. Okay. So, K2 is a constant whose value depend on the particle shape, as it is same for all other cases, and ds is also known as the Sauter mean diameter, and it is the diameter of the particle with the same specific surface as that of the powder. Specific surface means the surface area to the volume. So, then it is also represented in the mass fraction basis. So, ds will be summation x1, which is 1 divided by summation x1 by d1, that is summation of x1 by d1. So, 1 by summation x1 by d1 will be the representation of the Sauter mean diameter. Then the size of the particle ds dash, which is such that if all the particles are of the size, the total surface area will be the same as of the mixture. So, in that case K2 into ds dash square into summation n1 will be equal to summation of K2 n1 d1 square. Okay. So, in that case the ds dash will be root over summation n1 d1 square divided by summation n1, and also if you substitute the n1 with the value of x1, that is the mass fraction basis. So, ds dash will be root over summation x1 by d1 divided by summation x1 by d1 cube. So, there are many representation of this. Another is the length mean diameter, that is dl represented by summation of x1 by d1 divided by summation of x1 by d1 square. So, a mean length diameter or arithmetic mean diameter may also be defined by dl dash into summation n1. So, all the particle having this size will be equivalent to summation of all the individual particle n1 with the size d1. So, this may have of different size and different length with equivalent with the size of dl dash, which is the arithmetic mean length. In terms of in terms of mass fraction, if you want to express them, so that will become summation of n1 d1 by summation n1 or summation x1 by d1 square divided by summation x1 by d1 cube. Now, we will solve a problem on that. A sugar crystal has the form of a rectangular prism with dimension of 1 into 2 into 0.5 mm. Calculate the diameter of the sphere having the same volume, the same surface area and the same surface to volume ratio, which is called the Sauter diameter. So, we need to calculate the diameter of the sphere having all such characteristics. So, what we need to do, first volume of crystal, that is we need to calculate 1 into 2 into 0.5 because this is one rectangular one. So, we have calculated 1 mm cube. Now, surface area will be 2 into this dimension 1 into 2 plus 2 into 0.5 plus 0.5 into 1. So, all three sides we have taken multiplied with 2. So, we are getting 7 mm square, this is the surface area. So, now we have got the surface area and also got the volume. So, first is that with the same volume. So, same volume, if we want to calculate volume 4 by 3 pi r cube, we can convert this to pi d cube by 6 in that form and put the volume here, because it should equivalent with the volume of this crystal. So, this is 1. So, we are getting 1.24 mm, okay, cube root over 6 into V by pi. So, we are getting this. Second is diameter of a sphere with same surface area. So, surface area is 7 mm square, okay. So, pi d square. So, here we can get 1.49 mm. And the last one is the sorted diameter, that is ratio of the surface area to volume. So, we know that surface area we have got 7, volume is 1. So, 7 by 1 is the 6 by DSV. So, sorted diameter will be 1.17 mm. So, we can also try to identify that which area is coming minimum, which dimension is coming minimum if we take the different specific equivalent diameter. So, what is the minimum diameter in which case it is coming, that we can calculate. Now, food material often consists of particles of different size. To characterize such particulate material, it is necessary to determine their particle size distribution, as we are doing now. So, methods for determination of particle size distribution include many that we have discussed already. Out of that, sieve analysis is the simple technique commonly used for the determination of particle size distribution of the quantitative evaluation of the fineness of the powder. Okay. So, this is the sieve analysis set look like. Weight amount of the material is placed on top of a stack of the nested mesh sieve with opening size decreasing from top to bottom, and generally this sizes changes with a power of 2, sometime root 2 or 2 to the power 1 by 4 like that, and the assembly of sieve is mechanically shaken or vibrated for a period of time. The amount of powder retained on each sieve is then weighed and recorded. So, particles are counted based on arithmetic or number mean distribution, or also the mass mean distribution we can calculate. Then a frequency distribution curve, as I mentioned, that dx by dt with particular size is plotted, and which give the particular particle size, the percentage of the total particle either on number or mass basis against that size. So, that we can identify that which is the mode of that distribution. Alternatively, the data can be plotted as a cumulative distribution, in which either the cumulative percentage undersize or the cumulative percentage oversize is plotted against the size. Okay. So, if we see that this particle, sorry. So, here we can see that when we see this curve, so we are getting 50% of the size lower than this particular, okay, or if we this one is the undersize, and if we go by this curve, so we will get the percentage oversize of that particular material. So, like that for each size, if we suppose get this one, that means suppose we get this size. So, that means this much fraction has already passed through this particular diameter opening. So, that way we can analyze. So, both the way cumulative mass fraction and frequency distribution is done, and from this we can get very good insight of distribution of the particle in terms of how many fractions are dominating, which is the maximum size, which is the mean surface diameter. So, many conclusion we can take out of this particle size analysis, particle size distribution analysis, right. So, we will stop here and we will continue in the next class. Thank you.